Okay, so let's just go back and remind ourselves that we're starting on rotation. And what this does is it takes our particle in a box, which hopefully is rather boring at this point. I hope you're over all the hard things that you could have ever run into. Okay, so I've got a particle in a box, and it's trapped because it has an infinitely high potential. And we were able to figure out the wave functions because we had to figure out the de Broglie wave. We knew that sines and cosines, in this case a sine is the right answer. We inherently know that. We know that we have to have a de Broglie wavelength. That, of course, gives us the momentum, and the momentum will be kh bar. It's always that for, oh, wait, that's for a free wave. That's for a free wave, isn't it? It's actually n pi over L for a particle in a box. But anyway, so we're able to figure out wave functions, de Broglie wavelengths, momentum, yada yada yada, free waves, particle in a box.
Question. That's a good question. If it wasn't infinitely strong barrier, was the wraparound still possible?
So there's only an infinitely strong barrier here. And so what wraparound are you talking about? Well, okay, so when I go from here to here, so let's talk about rotation, right? So again, I'm hoping that you're over this. I think the hardest thing you had to do was this question, right? And that kind of slays you on the exam. So hopefully at this point we've done enough practice that that's not too hard. So let me just reiterate. I'm hoping that this part is incredibly easy and trivial at this point. So now we're moving into rotation. Now, when I said you go from here to here by kind of wrapping around the track, that's just an analogy. It should be, it is, hopefully it's a good analogy, but you would not use a finite box to use that analogy because it's nonsense. The reason is that the track, when you're doing, so we're doing 2D, so this is technically a 2D rigid rotor, and I haven't used those words yet because I'll explain why in a moment. But so what we're technically doing is a 2D rigid rotor as we introduce rotation. And the thing to understand is that we still have our, let's call it an electron, it's always an electron. It now exists in a universe that is this circular track. And there's not like steps in the train, I'm just drawing wave functions. Remember that what I've done here is I've, so I guess, one way to maybe to make it even more analogous is everywhere except in this thin track, the potential is infinitely high. Maybe that's a way to think of it. So maybe it's like a 3D object, but everywhere except this circular, this two-dimensional, infinitely thin disk, the potential's infinity. Regardless, yeah, does that kind of answer your question? Yeah, it's just a kind of way to get started on this. And I'll explain why it's called 2D. I've explained rigid rotor. I'll explain that in a moment. Other than, it's basically like here's our electron. Think of it like it's attached to a string of length r, and the string can't stretch, it can't compress, so it's very rigidly attached to that. Now, here's another way that it's similar, maybe not. So remember I was saying that these problems are mostly like particle in a box, but they do have a little bit of free wave character. Here's another example of how it's like a free wave. It's a completely ridiculous example because quantum mechanics is only important for things like electrons, and that's because it's very, very light. But I can't put an electron on a string. There's no way I could ever tie this thing up and spin it and just have it only stick to that length. I mean, it's just absurd, right? So it's a bit of an absurd example, but like the free wave we started out with, this is way easier than anything else I could possibly do, so let's do that, especially because this is a little bit harder than free waves and particle in boxes. Yeah, we're okay? Any questions? So, all right, now, last time I started out defining wavelengths, and again I borrowed some imagery from the particle in a box. I was then able to figure out the new type of momentum we have, Remember that angular momentum is r cross p, and I drew that last time. We're only working in the z direction, and don't worry about that, it's kind of minor for right now. We're going to finish this up today and then go on to 3D, which is more real. And so the angular momentum is our new quantum number, m, and I will make sure I have to write mass out from now on, because m used to be mass, and now from now on it will be the quantum number of rotation. And okay, so that's all that I covered last time. Now, one thing I'm basically going to repeat all of this today, but I'm going to do it more correctly by solving the Hamiltonian. So remember, I did this by drawing, kind of drawing what I had with a piece of paper yesterday, and it's all correct. But it's I've told you many times, quantum is weird because you almost never use the Schrodinger equation to solve the Schrodinger equation. Incredibly weird. But today I'm going to solve the Schrodinger equation, and we'll do some trickery with that to basically come up with the same thing. I've already told you what the wave function is, but anyway. Okay, now to do that, here's our coordinate system. So we have r, phi, so theta, which we're getting into in the next lecture, is this guy, but we're just going to hold it at 90 degrees. What's sine 90? What's sine of 90 degrees? 1, right, so it doesn't do anything. I'll actually show you when we do in the next hour, when we start to do 3 dimensions, I'll show that 3 dimensions turn into 2 dimensions if you hold the theta. Remember, this one's theta. If you hold it at 90 degrees, our 3D Hamiltonian turns into the 2D, which is sensible, and I'll show you that at the beginning. Okay, regardless, so we're not in spherical coordinates, we're in cylindrical coordinates, so we only have two deals. Again, theta is just at 90, so it just doesn't matter. I showed you last time how you get to this, which is a little bit of a pain, and it took a bit of a board. And I want to point out that what you're doing on your homework is, I spent the entire, about 20 minutes and most of a board solving this. Unfortunately, kinetic energy is double derivatives, not single derivatives. This is just the first derivative. And a double derivative, and one of you was asking me this, like, hey, wait a minute, is that, double derivative, is that the same thing as this? Think about how you solve this, right? You do one derivative and then you take the result of that and do it again. So yes, it's fair to say that this is this, and that means that to solve for the double derivative of x, you're doing this, just doing the same thing twice. And if you've looked at the homework, you have noticed that the question is all about, half of it, like questions 1 through 5, is just this. And so what do I want to say about this? So the hard part is that you end up with it's quadratic, it's x plus y squared, so you've got x squared plus y squared plus xy, yx. You have to be careful about going in order. So you've got this operation in front of this operation, you've got this operation in front of that operation, and the other two, right? And you've got to be careful about how you do this because like this one, if this one's in front of this one, I can see that I have some problems. I'm going to simplify it because I've got an r there. I have an r in front of a derivative with respect to r. I have to be careful about how that works. When this one is in front of this one, I don't have that, right? I've got an r in front of a wall, but the wall is a phi wall, so the r can pass through it. So you see why this can get a little complicated. Now, unfortunately, because today is Double Lecture Friday, last year, because of when school started and yada, 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 I actually had the extra hour, and I basically worked the question. But this time, today's double lecture, so I can't do that. Oh. So, well, I know what you're asking, right? What I do with the video, I just deleted it. Right, that was the only thing that made sense. I was crying when I deleted it, because what it could have done is just uploaded it to the resources section on the website. Okay, so I uploaded it to the resources section on the website. Okay, so what I did last year, again, because it worked out that I had the extra hour, as an extra hour last year that I did this, I basically worked through the problem on the board, but I can't do that this time, but the video is on the website. And not that that really, this is one of those times, it doesn't help you to see the answer. But that's why I don't mind doing it, because just writing it down will get it through to you. Another purpose of making you do this, by the way, is not also just to get you, mathematically oriented, which again is all research has shown the best worker you will ever be, the most paid worker you will ever be, is the most mathematically oriented worker. So I'm trying to push you in that direction. Also, I want to get you used to R, theta, and phi coming out of your ear. It's just like, you're bored of this, right? It's like, okay, now this is trivial, right? I'm trying to make you the same way with R, theta, and phi. And the way to do that is to basically just bum rush you with unbelievably large number of questions. So anyway, so that's on the handout section, which you should be looking at because there's a couple of things on there. And hopefully you didn't forget that. Okay, so this ends up being, oh God, where do I have? Hold on, let me find the whole answer. Okay, so minus h bar squared over 2 times the mass. Remember that 2 hours lecture 2 Fridays ago. 2 Fridays ago, I did a lecture on second order differential equation. And sorry, no, it was the last extra Friday. I'm just trying to think about the schedule. Last extra Friday, I did 10 minutes on multi-dimensional quantum. I did a multi-dimensional particle in a box. So again, you really do need to watch that. It's only an extra 10 minutes. I just messed up by letting lectures spill over into the next hour, which I'm not really supposed to do. But anyway. Okay, so this is the correct Hamiltonian for kinetic energy, Hamiltonian. The potentials we're not doing potentials because this is the correct Hamiltonian for kinetic energy for 2 dimensions. It's a 2D rigid rotor. You go through this nightmare, and what you end up with is minus h bar squared over 2 times mass times, okay, where am I at? Okay, so now again, you're going to work through this on the homework. And there's actually something kind of really cool that comes out of this. And I'm thinking about putting a question like this on the exam because I have to start writing it this weekend, which I will do because I kind of have to. And I will, of course, start telling you stuff about what's on it. And of course, Wednesday is the review, and of course, I will spill tons and tons of hints. I also just want to point out something. This is just algebra doing this, but I mean, look how easy this is. And remember the extra hour last Friday? I showed you a 2D particle in box. It's really easy. There's really nothing much to this. Look how complicated that is. I've got a double derivative, a single derivative, a double derivative. What? I've got the terms mixed up right here, one over r squared with a phi in there, all mixed up. It just comes out the way it comes out. I mean, if I was a freshman in college, having had my first year of calc, I would have said, oh, well, the double derivative of x is the double derivative of y is the double derivative of r plus the double derivative of phi. No, that's kind of, in retrospect, childlike. This is what it is. It's kind of complicated, but what are you going to do? It's just how it comes out. Okay, so now that we have the correct Hamiltonian, now I'm going to do something, and again, this is a good question for a test because it ultimately shows you really know what you're doing at a deep level, yet is simultaneously shockingly simple. So, this is a rigid rotor. I haven't used that term because I need to use it now. We also know that a wave function, and I'm in 2 dimensions, so I need to have 2 variables. Again, watching the lecture 2 lectures ago about multivariable second order differential equations, you know that I'm hopefully going to be able to do this. I should be able to put the answer like this. But now let me ask you this. What is the point is the point of this if the particle always revolves around the track with the same r? What can this tell you? It begins with N and rhymes with a thing. It's nothing. It tells you nothing. You see, the thing that remember, this is a probability distribution. It should tell you, yeah, you know, you have some probability of being 1 nanometer radius, and maybe there's some probability of being at a 2 nanometer radius, but again, very unrealistically, but whatever. This electron's got a leash on it. It is always, let's say, 1 nanometer. It's always rotating at 1 nanometer radius. So what is the purpose of this? Another way to say this is that it's always a constant. Maybe it's just 1 nanometer. It wouldn't have units, but let's just say it's 1. Okay, so then R, if R is a constant, and again, I force it to be a constant, then this is 1 over 1. And what's the derivative of a constant? 0. Right, so, again, you see why we like to start with these simple, albeit unrealistic. So if R is, so again, you definitely want to write this down. And I'll come up with some snarky question that's similar, but not exactly the same because that's trivial. Then, all right, the wave function doesn't really have any information. It basically, you know what they actually become? There's a few times, you'll actually see this one other time in another example. It just basically becomes a normalization constant. It's just, yeah, that's basically all it is. Okay, it's a constant, so there's nothing in there. It just ends up going into the normalization constant, which doesn't really, just not that important, really. And if that's a constant, then the derivatives, double derivatives, whatever, just get rid of them. They just won't do anything. So not that they're equal to 0. A derivative is not equal to 0. A derivative is a derivative. I'm just telling you, since it operates on a constant, it'll always just be wiped out, so you might as well just get rid of it. Just don't write it. And I'm just doing this just saying this for shorthand. Okay, so therefore, the Hamiltonian on the wave function is now minus h bar squared over 2 times the mass. Now you know that's about to turn into the moment of inertia, and it'll turn into the moment of inertia because sorry. Not the, what about that one? -1. Right, the 1 over r squared. Well, now I don't really know what r squared is. I just called it 1 just because it makes the conception a little easier. I haven't really defined it. So, so I'll just still call it r squared. But maybe, yeah, it still could be 1. I just haven't necessarily defined that yet. So all of that turns into this, which is now minus h bar squared over 2I, where I is the moment of inertia. There we go. Mass r squared, moment of inertia. You had it in mechanics class, in physics mechanics, and there you go. So it ends up being kind of easy, and again, because it's a simple example problem, you just get kind of lucky. And I'm supposed to add a wave. Here, let me do that. That actually solved my problem. Sorry, I need to add a wave function to it now, right? So, okay. So why don't I start doing that? Well, here, let's figure out what wave functions are. And these are wave functions of the Hamiltonian. It would help if I looked at my own notes. Okay. Double derivative. So the wave function has to have a phi in it. And again, there's an r in there too, but it just is a constant, so it doesn't matter. So I need a function that I take the double derivative of. Here, I'll write this out so that it's more clear. I didn't mess that up last time. Oops, why put a pi? Why did I do that? 2I. So one reason we use an I is that mass it disappears when you do that. Okay, so I'm writing this out this way so that it is obvious to you. What I need is, I don't know if you've ever seen this before, I need a function that I take its double derivative and I get the function back. Yeah, what was that?
You needed
Yeah, right. You're seeing the free wave. You're seeing not the particle in blocks. I'll explain that in a second. You're seeing the free wave. But remember that 2D rigid rotor is like it's part particle in blocks, it's part free wave, and there's technically no potential energy. That's why it's a free wave. This is where it's actually got free wave, free particle wave functions, free wave functions. And I'll explain, we'll look at that for quite a bit, but again, don't write this down yet, I'll explain a little bit later. Cosine and sine actually will not be allowed, and that's for this really cool reason. So the answers are going to be e to the I phi, e to the minus I phi, so that's going to be the answer. Not sine and a cosine, I'll explain that in a little bit. Here, I think I need to go ahead and use the other board, which, and you know that this is when the dinosaur walks past me. If you watch the videos, it's always when I'm erasing the board. What do I want to say about this? Okay, so I know that an e to the I phi is going to do that, but it's still got to be consistent with the de Broglie relation. It's still got to have the de Broglie wavelength in it, and I've got to get the right momentum. Remember, I worked out the momentum last time. It's the quantum number, m, times h bar. So I've got to engineer the wave function to do that. Not that I haven't already, but regardless. Okay, so what I propose is the following. Now remember, so there's a normalization constant. I'm not putting that up there yet. Do I want to put a, I don't think I want a minus, no, I don't want a minus sign. Okay, so you know that, of course, e to the I, insert variable, there's only one variable. But now, here's what I suppose is, it has to be perfect, blow up. There we go. It's got to have the quantum number in it. Normalization, we'll solve the normalization in a little bit. You actually did it on the previous homework, by the way. I did that to make this a little bit easier. Regardless, let's see. Does this give the right energy? Let's see. Minus h bar squared over 2I. I keep writing a pi for some reason. I don't know why. Okay, let's do the double derivative of the wave function. And of course, what we end up with is minus h bar squared. I squared, so that gets rid of that. H bar squared, m squared over 2I. Psi, so this is in the energy. Now, if you recall, I mentioned that in mechanics class, you learned that momentum squared over 2I was the energy of rotation. So J squared over 2I. Now, since we're only in the z direction, I always include a little z there. And last time we found that momentum, angular momentum, remember, was m h bar. We got that from looking at those wave functions I drew on the board. We figured out that had to be we figured out the de Broglie wavelength and whatnot, and that led us to this. And yes, of course, they're the exact same thing, so that makes sense. Okay, now we can get a little bit more out of this. Now remember, I won't write this down, don't write this down, just remember, when we were doing free wave and then we started doing like your homework, what are the K's for the free wave? The K's are always square root of 2me over h bar squared. Maybe the potential messes that up. Okay, so here, okay, so here, I'll do it this way. Okay, so h bar squared m squared 2I is equal to the energy, and therefore m is, and this actually does something really kind of neat. 2I. Am I doing this right? I better, yeah, 2I. Yeah, over. Okay, since you square it, the square. Always a bit of a problem. The square of -1 is 1, and the square of 1 is also 1, so plus or minus. Remember that we had plus or minus m quantum numbers because the thing can turn right-handed or left-handed. Those are equivalent and degenerate. Remember that there has to be degeneracy because we're multi-dimensional. That's nothing but factoids, right? Why you have to watch this over and over and over and over and over again. Okay, now remember that also the way our wave functions work, which I'm regretting having taken this apart. Here's the ground state, and the first state was like this. So anyway, from the de Broglie wavelengths that we got last time, we also know that m is 0, plus or minus 1, plus or minus 2. If you forgot, again, watch, I did upload the last wind state video, it's on the web. So again, recall this. Okay, look what the energy does, right? So I always thought this was kind of neat. Notice that energy has to mess with the moment of inertia, and h bar just is there. It has to be of a certain value such that this jazz ends up being a whole number. So that's quantum mechanics. That's the quantum in quantum mechanics. The energy just can't have any value. It has to have a value for which this whole mess is 0 or a whole number. And of course that means it's like, you may be thinking like, well, gee, the energy is really tied down to some very specific values. Quantum mechanics, exactly right. So now, if that wasn't super clear before, which maybe it wasn't, hopefully it is now. So again, sometimes I look at this and I see this mess of numbers, but when I think energy, I absolutely know what that is. And it has to be a certain value to make this happen. I'm like, yeah, I get it. Quantum is all about constraining things. Boundary conditions cause constraints that's the result. Okay, now last time I did this by making these silly drawings with my piece of paper, but now I have a whole other way to do this. Remember, I just said that the quantum and quantum mechanics is, these energy levels, ground state and infinite number of higher excited states, comes about in the boundary conditions. Now I'm going to do this by the boundary condition way. Last time again, I said that there's only certain waves that follow this track correctly, and that led to these conditions on M. But now let me do it more mathematically, not just via some silly drawing. Okay, the way the boundary condition works on the 2D rigid rotor. See, I can do this now that I have the wave functions. That's why I had to start with drawings. Okay, the boundary conditions of smooth and continuous. We can actually just do continuous. That's enough in this case. Is this? The wave function has to bite its tail. After it goes all the way around the track, it has to still equal itself. The smooth part, by the way, if you get continuous right, smooth is automatically right. So that's why I don't have to worry about the derivatives being equal. Once I get this part right, then the derivatives are automatically equal, just kind of mathematical magic. So that's why this is, maybe for the first time, this is actually slightly easier in this one respect. Okay, now that I know the wave functions, I know that this is e to the I, am I forgetting my m? Yeah, Im. Okay, phi plus 2 pi, because again, 2 pi is you've gone all the way around the track, and of course you better equal e to the I m phi. Now, basic knowledge of exponentials, e to the I m phi, e to the I m 2 pi is equal to e to the I m phi, means that that this thing has to be what? Use of the board is not good. It has to be what? 1. Right, 1.0. Okay, so again, now I've got a boundary condition. Now what does that do? I'm not using the board super well. Okay, so if e to the I m phi is 1, and phi can be anything, that's how I knew I had messed up, because I said phi can be anything. And I knew that doesn't work. If e to the I m 2 pi is equal to 1, tell you what, let's say I often put this on the test, so I probably can't because I'm going over it, but let's say you're at the test. Let's calibrate ourselves as though we're on the test, although I can't specifically ask this question. Maybe I'll ask a similar one. You look at the cheat sheet, and you see e to the I minus I 4 pi is e to the minus I2 pi equal e to the 0 equal to dot 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 are all equal to 1. Therefore, m is equal to no, 0 plus or minus 1 plus or right. We just did it. Dot dot dot. Right. I only wrote a couple of these. I don't have enough room. Right. So any whole number. I just wrote a couple of these. So, sorry, I think that misled you. But anyway, e to the I whole number pi, including 0, of course 0, is equal to 1. So the point is that we did this before from a drawing, and this time we did it from the way I really ought to be doing it, was mathematical analyses of what I've been telling you. You've got to follow boundary conditions, and so the boundary conditions put restrictions on m, on the wavelengths, and then of course that puts restrictions on the energies, because the energies have to make, the energy has to be a certain value to make that true. So now you see that. Okay, so now this part's kind of cool. I'm going to tell you something really, really messed up about wave functions. And the way, I'm going to get into more cosmology stuff. I won't necessarily talk about hadrons versus leptons, unless you want me to. Electrons are leptons, by the way. Hadrons, I believe, are protons and neutrons. And I know all this from watching YouTube videos at night. Although sometimes the cat falls asleep on my face. You hear Charlie throwing up. Okay, so what do I want to tell you? Okay, so that's really about all. I think that's about all I have for real. There's not much else to do. We'll do a angular momentum in a minute, but question.
Sorry, quick question about that. The negatives, do they come from the m? Like e to the negative I 4 pi?
Yeah. Well, here. Let me tell you what. Let me just write down a couple more so that I just didn't write down enough of these. Here, let me just write down minus I 3 pi, e to the minus I 2 pi, e to the 0, e to the I pi. Wait, let me make sure. I'm wondering whether even odd works. I got them in my notes here. No, sorry. Only even numbers. That's why I was freaking out there for a second.
You showed us in the last lecture that the odd ones, they have a cusp.
Yeah, the odd ones have a cusp, but the reason that I messed up there is that the 2 is right there. So that's why I don't have a 3. Okay, 0, I 2 pi, I 4 pi equal to 1. Okay, so now you see why m, these should show you that m is 0 plus or minus 1 plus or minus 2. Plus or minus 1 gives you, minus 1 gives you that and that. Minus 2 gives you that and that, right? So I know I just need to write them all down. I'm being lazy. Other questions before we go on? Okay, so now let me tell you something that's really kind of cool. Okay, so let's see. I don't even know how to begin with this. Okay, so let me just say that. Okay, what about that? Right, double derivative of sine. Oh, I guess I should have it down. Sorry, I should have it down. I'm not trying to fool you here. And a normalization constant. Let's not worry about the normalization constant. I'll show that in a second. Okay, so what about that?
Is negative m squared sine on...
Well, I mean, does it not work? So I just showed you the wave function is e to the I angle. But what about that? Now remember the free wave, you had e to the I, e to the minus I, and I have that too. I have e to the I. M can be minus. So I have e to the I, e to the minus I. I had, for rotation, analogous to the free wave had e to the I, e to the minus I, but it had sine and cosine. So what do you think? I mean, it's just double derivative, right? Wouldn't this work? The answer is you reject. You reject it out of phenomenological grounds. So remember that mathematicians give us tons of answers for quantum mechanical problems, but we have to take responsibility for rejecting some of them. The government. So the reason is okay. Okay. Here's another little neat thing about. Let's do free wave. Now remember that when I say free wave, I'm talking about a single particle, an electron on a track, right? That goes to infinity. Okay. Can it have no energy? Can it choose not to? Let's say it's moving to the right, so that means that it's an e to the I k x. Can it choose to not move? Yeah. Well, what would k be? K is definitely related to kinetic energy because m squared k squared over 2m mass, 2 mass is the energy, which is all kinetic. So could it choose not to move? So it's moving to the right, but could it slow down and just basically stop? Sure? Now the answer is yes, it can. It can slow down infinitely slow and stop. Right? And k can be arbitrarily small. Now you're confusing the particle in the box. The particle in the box, that thing can't stop because of the uncertainty principle. Remember that because its position becomes localized, it has to have finite kinetic energy. Right? Remember that? Because it is trapped in a box, it has to have some uncertainty in speed. The only way to have uncertainty in speed is to have speed. If it's not moving, you know kind of where it is, and you definitely know how fast it's going, but you can't do that. You can also, and again, this is an explain with words question and answer. I can also do it mathematically. Question?
Sure. So, where is that thing's kinetic energy going?
Well, now remember that this particle exists because God created a one-dimensional universe with nothing in it and chose the particle to basically have no kinetic energy. And,
okay,
and it's okay.
So it didn't start out moving. It just was never
Yes.
moving.
Yes. Remember, as soon as the great turkey in the sky creates this one-dimensional universe with nothing in it that goes on for infinity, the great bird God decided the energy, and it stayed that energy. Okay. And it could be arbitrarily low. Now, what about the particle in a sphere? Can it choose not to rotate? Can it rotate with no rotational energy?
Well, it won't be rotating. It'll just be moving straight.
Well, it won't be rotating, but it's still in this weird, the bird God created a two-dimensional universe that wraps around itself because that's what the bird God wants, and that's good. But can the particle choose not to rotate on the track? Yes, right, because we have m equals 0 as a solution. Right, just like k can be arbitrarily small, we can have m equals 0. So the particle can choose not to rotate. And I have a solution for that. And it's also, if the particle is moving to the right, it could just be moving arbitrarily slow. Now remember, the particle in a box does not have that option because it got localized. So that's kind of funky there. That's where the particle in a track is not like a particle in a box. Okay. Now, but there were two ways. You could either say basically have a k of 0, or you could have a sign. You could do that. But what's your interpretation of that? Remember, I said sines and cosines. It has. Let's make the k not 0. It's pi or something. Who cares? It's just not 0. So it has kinetic energy. So tell me, why is it still not moving? Now think back to the exam. What's the momentum if the free wave is a sine?
Oh, 0.
Right, it's 0. Remember that it can be moving simultaneously right and left. It can move simultaneously right and left, so that while it does have a finite k, what happened is the reason that you have to choose a sine or a cosine is the turkey god told you I've created an infinite universe in one dimension, there's a particle, and I gave the particle kinetic energy, but I'm choosing not to tell you what direction. If that is the problem that you have to solve, you have to use a sine or a cosine. Neither is fine. So that's a little weird, but anyway. So that is what you use this because it's the right answer to the problem you're presented with, all right? Now, I'm telling you that you can never do that with a 2D rigid rotor. Now, the reason is not because it's not moving. I've got a solution for that. I got m of 0. But I'm asking you this. So the analogy would be, okay, so the analogy, okay, so for your notes, so in case when you're reading your notes you don't get lost, it's equal right plus left. Okay, so the analogy for 2D would be that the wave function is an equal part, and I'll draw it so that it's like a little easier. This plus that is equally moving left and equally moving right, rotating left-handed and equally moving right-handed. That would be the analogous, that would be a sine or cosine or whatever. Not important. But I'm telling you that, no, you cannot make that choice. And again, it's a phenomenon, no, it works mathematically, but it is the wrong phenomenological answer. You cannot make this choice. Now the reason that I'll maybe spill over into the next hour, the reason's insane. The reason is that, remember how I said you had to make this choice because the great buzzard created a universe with the particle but chose not to tell you whether the particle was moving left or right. Okay, now, Apollo creates a particle in a rotating track and chooses not to tell you whether it's moving right-handed or left-handed, but you have an option that you didn't in the one-dimensional universe that you do in the two. You can shine light on it. You can shine circularly polarized light on the particle in a 2D track and distinguish. They can be distinguished. So while you may create a universe comprised of a one-dimensional circular track and put a particle in it, and choose not to tell your minions whether the particle is moving right-handed or left-handed, you have the option of using light to distinguish between the two. So just because you don't know it doesn't mean you can't know it, you just have to do an experiment. You shine light on this, and you would either absorb right or left circularly polarized light, telling you whether it's moving right-handed or left-handed. So if it's like, now I'm not quite sure if this is 100% correct, if it's moving right-handed, it probably absorbs right circularly polarized light, but not left circularly polarized light. In other words, there is an experiment that will allow you to do this. A free wave, without knowing which way it's moving left or right, actually it doesn't matter. You cannot shine light on this. It actually doesn't absorb light. A particle in a one-dimensional track that goes on forever does not absorb light, and that gives you no ability to figure out whether it's moving left or right. But a particle in a 2D circular track does absorb light, and then you can figure out whether it's moving left or right, meaning that sine or cosine is never an allowed answer. Right, cross it out. It's never an allowed answer because you can always distinguish the two. Okay, before we take our break, why do you think that is? Why does this never absorb light? But just take the same damn thing and turn it into a circle, and then it does. Why does that happen? Well, now, okay, so light has energy, right? So it'll have to go from ground to excited state. These things have excited states. I know rotation has excited states. We just solve for them. But what else does light have? It has momentum, right? It has momentum. That's h over lambda. And it has angular momentum. Light has two forms of momentum. Remember, it has momentum because it's doing that. Right, that's good. That's, remember, photoelectric effect. It hit those electrons. Cat was throwing up. But anyway, but remember, I was also telling you that it also does this. Remember this? Right and left circularly polarized light? you've got to account, remember that the nature has a couple of fundamental laws. Can't go faster than the speed of light. Energy is conserved, so is momentum, and there's two types, linear and circular. Light has both. So this guy can absorb the hit momentum and the rotational momentum. This one can't. For one, it's not rotating, and number two, it only lives in one dimension, and rotation can only happen in two. So it can't absorb the rotational momentum multiple ways. All right, so next class, I'm going to solve that. And then the last bit we're going to do is uncertainty principle on the 2D rigid rotor. And then we'll do three-dimensional rotation. So I know I went over a 10-minute break. And